Since the release of Supersonic Desktop, I've had a few conversations about how to do a rooftop noise analysis in Supersonic, and so I thought I'd put together a little demo for you right now. Before we get to the rooftop, let's talk about an ASTM E336 noise transmission loss calculation or measurement. Inside a building, you would have two rooms, the source room and the receive room, and then you'd have the partition under test in between those two rooms. In the source room, you'd put the loudspeaker sort of away from the wall in the far field, we would call it, and you would measure or scan the source room away from the speaker past what we call the critical distance, which is where the direct field and the reverberant field meet up, and you try to measure in the reverberant field because you're trying to get a constant sound level in the source room against that partition that you're testing. In the receive room, assuming that it's within a certain room volume, you can scan sort of the middle of the room and get the reverberant field in that room to create the subtraction that you need to do to determine the transmission loss. So there's this interplay and consciousness that you need to maintain of the direct field and the reverberant field. On the roof, there is no reverberant field. We have a direct field, but outdoors we generally call that the free field. And so on the screen behind me, you see a roof plan with RTU1 that we're going to take a look at today. And this is on top of a school. And the red box indicates the classroom that's next to this unit. Now, this project didn't start off with a condensing section on the air handler, but it's ended up there now. And we need to test, we need to calculate and see what is all required because of the condensing section that is right next to that classroom. This is a 16th inch scale plan that I've already set up, and I can go through and measure here and see that we're about 4 feet away from the edge of the unit, if we want to consider that to be the edge of our point source. We'll start there and see where we go. We'll consider this isn't a quite perfectly a square, but let's consider this to be a 30 by 30 foot classroom, and we'll get into that as part of the calculation. Just a few more of the details of the unit. It looks about like that in a picture from the cut sheet, and the noise levels are here. And what we're concerned about today is the radiated noise levels. I've already prepped those values in Supersonic. You see the air handler that I've placed here, and we're most interested in the casing radiated noise levels, again from the table I just showed. So we have the sound power levels associated with the unit, and now we want to take our sound power level and we want to understand what the direct field or the free field is some distance away. So we're going to be converting to pressure along the way. So this calculation block starts us off to do a distance calculation using a sound power source. So we'll connect our radiated to the source and click into the box, and we will give ourselves a distance. We said 4 feet. That's to the edge of the classroom. We might be able to add a couple more feet just to get into the classroom a little bit, but we'll stay there for now. We're going to use a directivity or a Q of 1 because this isn't necessarily a reflection off the roof. We're looking at the transmission into the roof. And in exterior to interior calculations, you might use a value that takes a look at the incident angle. We're going to ignore that for the time being right now. That's not yet in Supersonic. But with the 4 foot distance away with a spherical calculation, we have a sound power to sound pressure loss of 13 dB across that 4 feet. Let's now add our transmission loss using a sound pressure input. Now remember, in the room-to-room test that I spoke about a little bit ago, you're using a sound level meter, and so you're already measuring sound pressure inside the source room and the receive room. So we can use pressure on both sides of our transmission loss to understand what is happening on the roof above and then what's inside the building. Let's connect our sound pressure output of the distance loss to the input there. Let's add a room alpha, and I'm going to use the common rooms from ASHRAE that may or may not be appropriate for your particular environment, but I will connect the room alpha there, and I haven't necessarily given that a value yet. Let's call it average. So it's going to have an NRC of 0.25 average for the room. Now we need to add transmission loss that we are associating with this roof construction. There's a few different sources you can use depending on what your roof construction is. Today we're going to use an NRC report that shows, it's from their facade elements report, and it is for a built-up metal deck roof with a 1/2 inch or 13 millimeters of fiberboard on top. We can sort of think of that as Den's deck or a cover board. And it has ACT below, some distance below. Looks like 350 or so millimeters. The transmission loss values are here along the left, and we'll use that in our calculation. By the way, this report is great if you're not familiar with it. There's values for this built-up roof with the ACT. There's one without the ACT. And then there's not concrete, but there's river wash pebbles or a ballast roof without ACT and with ACT. And so this is a good report to have. It's the NRC IR818 is the number of this report. So I've plugged those transmission loss values into this block right here. And let's go ahead and connect it to our transmission loss block, which is actually more appropriately a noise reduction block. Since we're using the transmission loss, we're doing some manipulation to it, and we're figuring out the pressure level differential between the rooftop and inside the classroom. We'll activate the TL block. We'll use our room dimensions of 30 feet by 30 feet by 12 feet tall. And then we'll look at the common surface area, or what the surface area is that's in common between the roof and the classroom. And so for 30 by 30, it would be about 900 feet. Now remember, this is a rooftop, and the sound level is dissipating as we move further away from the front edge of the classroom to the rear edge of the classroom. So we need to interpret a little bit what the source level is across the roof as we get further away, given that from 4 feet you get some significant doubling across that 30-foot classroom span. But we've given our room dimensions, we've figured out our common surface area, and now we have an overall loss of this block that we can compare to the transmission loss, and note just how it's changed because of the alpha inside the classroom and the common surface area, the proportion of surface area of the classroom that is exposed to the roof. And so now we have an output for this block of these pressure levels here below. Let's go ahead and plot that on an NC chart. We can connect the sound pressure output to the NC chart, and note that we have a problem, NC 49. And for a classroom, we would hope for an NC 30. If you're going for lead, maybe an NC 35 tops if you're pushing it. So we know we need something more than this transmission loss right now. Before we do that, let's take a look at what our distance loss gets us over the distance of the roof. Because we want to manipulate this to understand at what distance do we need to improve our roof before the distance overcomes the benefit that we need from the roof, and we can go back to this built-up roof construction that we are using the TL values for. So we can go to the radius here for our distance loss block, and I'm going to use my mouse wheel because with the mouse wheel I can easily increment and decrement the value and quickly see in Supersonic what I need to do to achieve my target level. And so right there I'm seeing I need 25 feet of distance to get to an NC30 inside the classroom. So essentially the whole classroom I need to protect from this noise on the roof. I'm not going to add another product or full transmission loss per se for this, but we can use, let's use mass law instead. With mass law we can plug that in as the transmission loss. Click into it. Look at the weight. Let's reset our distance back to let's do 6 feet this time instead of 4. And what mass law do we need? So I'm going to again use my mouse wheel and just scroll up until I get to NC30, which puts me at about 17 pounds per square foot. I need of total single mass, not considering the ACT, on my roof to get to an NC30 in the classroom below, admittedly with no factor of safety. One thing I will mention before wrapping this up today is that there is a transmission loss block that does take a sound power input. And you'll notice that it has an additional block here for the source alpha. And so you can take a sound power level of an air handler that is inside a mechanical room, let's say, and do a calculation with this. But to do that, this requires that the air handler be in the far field and only consider the reverberant field as part of your analysis. And so you would need to know the alpha of the mechanical room, the alpha of your receive room, and then you can do the same calculation so long as you know your source room dimensions, your receive room dimensions, and then the common area of wall or floor ceiling that is between the two spaces. So I hope you enjoy continuing to explore Supersonic Desktop. There's a lot here in the app, and there's a lot yet to be added to the app. You can download the latest version at 10log.io/products, and you can sign up for an account for the app at 10log.io/signup. I appreciate those of you who are supporting the app. A lot of work goes into it, and I hope to keep it going.